Want some homework problems?
No.
No. Do I want homework? I don't want any homework problems. No. I graduated a bunch of years ago. I didn't want any homework problems. All right. So, it's gonna be annoying if that little. So let's see. I mean, I could not give you homework problems to turn in if you'd rather not.
No,
You need the practice? Well, there we go. Okay. That was kind of what I thought. Okay. Oops, like that. I'll save the ones for out of 7.3 and 7.4 later.
Is that a 6? 7.2 dash.
It's 6, yeah, sorry. I don't know why I put those in different, weird order. Because it is 28.31 and 28.17. I don't know why I did that. I must have decided I like that problem later. That's not the one I want.
When is he studying?
31? What?
Can you clarify the numbers again?
Yes, it's a 31.
When is this due?
When do you want to be due? Friday?
Yes.
Okay. Well, it's either, I mean, it's either Wednesday or Friday, so. Friday's good. With break coming up, it's either Wednesday or Friday, so.
No, next one.
That's crazy.
Yeah, I know. All right. Well, let's do a couple of examples out of this packet that I handed out to you. So let's look at the 30.5. So the 30.5, they give you it's definitely a small sample size. However, they know that the sample's coming from a normal distribution. The null hypothesis is that the mean is 10 is going to be tested against the alternative. And they give you both the sample mean and the sample variance. It asks you to figure out what is your critical value, what's your t-value you're going to compare it against, and then your decision. So in this one, they tell us that the null hypothesis of the mean is 10, and the alternative is that the mean is not 10. So is this a one-tailed or a two-tailed test? 2, good. Yeah, because it's not equal to, it's a two-tailed test. So what does that mean for the significance level when we look for the critical value? What do we need to do to the significance level? Yeah, you got to cut it in half, right? Because remember, when we have a two-tailed test, we want those probabilities to be on the tails. We want those tail probabilities to total to 0.05 in this case. So we're going to have it, right? So when we look at the t-table, then we want to look up, you're welcome, the t sub 0.025 rather than the t sub 0.05. Okay? And then in this particular case, since we're doing small sample and it's unknown variance, I need to do t, right? Probably indicated by the fact that I've got t written all the way down for every answer choice, but in particular, I know it's a t-test, a t-table value that I need rather than the normal distribution table. Again, the thing that tells me it's definitely t, besides the fact that it's small samples, it's unknown variance. If we knew the variance, we would still go to the z table, the normal distribution table. Since we're going to t and it's a random sample of size 4, what's our degrees of freedom? 3, good. And the degrees of freedom are free. 3. So we want t sub 0.025 of 3. If I look that up in the table, what value do you see? 3.182. Good. So right away, we've eliminated 3 of the choices. Notice that choice C is that you forget to subtract 1 from your degree of freedom. That's the 2.78. Choice B is the fact that you forget to divide your 2 in half and forget to subtract off your degree of freedom. Choice A is you have the right degrees of freedom but forgot to divide your alpha in half. So you can see all of those are interesting distractors to have. Okay, so we good for the critical value? All right, so we're looking for the either to be above 3.182 or below negative 3.182 to be able to reject. That's how we're defining our critical region in this case, right? Just to write that down. So I'll write it as an absolute value statement. Absolute value of t needs to be greater than 3.182. So to calculate our t statistic then, we do our sample mean minus our purported mean over what? What do we divide by? Square root of something over n. Yeah, good. Okay, so the something in this case is the variance over n, because remember it's s divided by square root of n, or square root of s squared over n. Oops. So in this case, n is 4. Wrote an n instead. So we've got what? 5.84 divided by 2? If I did my arithmetic correctly in the denominator. So 5.84 divided by 2 is going to be what? 2.92? So in this case, do we reject or not? No, because we're not big enough. So our conclusion would be do not reject H naught. So answer would be D in this case then. Everyone okay? Let's look at 30.10. I don't know why. Yes.
For this problem, for example, what would be the probability that we're wrong, that we're saying rejected?
So remember that we should have if it's probably we should have rejected when we didn't. That's the power, right? That's a harder question to answer because of the fact that we're looking at the mean is just simply not 10. Right? So that's you don't know exactly what the mean would be in that case, so it would be dependent upon what the mean is. So that's one of the analyses that we're going to talk about later this semester. We're going to create what's referred to as the power function and then analyze that particular function. You could do it for individual things. So, for example, if you knew the mean was in fact 9 rather than 10, you could figure out the probability that you were wrong then, if you had a specific value. Power is a harder question to answer, which is why we're going to spend more time on it later. We can only really answer that question if we know what the actual value of the parameter is, which in practice you're not going to know, because you're trying to test it against something that's hopefully changed off of something, but not exactly know what it is. So that's why you have to do what are referred to as the most powerful critical regions, and try to make your critical region as powerful as possible so that you can try to minimize those errors. So, like I said, that's stuff we'll talk about later this semester when we get some more machinery behind it. Yeah. But just know that you're asking good questions and they're hard ones. All right. So let's look at 30.10. In this case, we've got two means that we're trying to test against. But notice in this case, they're paired observations. So they're not being drawn from independent things. They're being drawn from, they are actually paired with each other. So the x has a y, there's some relationship, probably some relationship between them. Remember, we talked about examples of doing the paired means when you were looking at maybe a weight loss program or a strengthening program, or those kinds of things, like a before and after idea. So those are where the paired observations come from. So the null hypothesis versus the alternative hypothesis, we're looking at the t statistic in this case based on the paired differences. Now, remember, for paired differences, we do the subtractions first and then do the means, versus looking at the means independently. So notice that what that's going to do for us is that it's actually going to change what the degrees of freedom are. So if we were not worried about them being paired, if we just had a sample of 3 for the x's, a sample for 3 from the y's, and they were independent, and you were checking to whether or not the means were different, or the difference of the means is 0, how many degrees of freedom would you have in that case? If you had 3 for the x's and 3 for the y's, and we're looking at the difference of the means, assuming they were independent and not paired. 4, right? Because it would be 6 minus the 2, right? Okay. However, since they're paired in this case, we do the subtractions and then the computations, right? So in this case, how many degrees of freedom would you have? When you do the subtractions, how many observations do you really have? It's not 6 anymore. It's what? After you do the subtractions? 3, right? So your degrees of freedom would be 2, right? So that's really what this particular problem's asking about, besides the other distractors, obviously, is whether or not you should be using 4 degrees of freedom because you've got 3 x's and 3 y's, or 2 degrees of freedom because they're paired. And in this case, it should be the 2 because they're paired observations. Okay? So when you look up your t, in this case, then, is it one-tailed or 2 when it says not equal to? 2-tailed, right? So we should be going to 2 degrees of freedom for 0.025, which gives us the 4.30. Right? And so 4.30 is bigger than our test statistic. So what's your conclusion? So the 4.10 is the test statistic. The t-value we want to compare it to is 4.3. So what's your conclusion? You got a 50-50 shot, right? Are you looking for bigger than 4.3 or less than 4.3? It needs to be bigger, and it's not, right? So it's going to be do not reject, right? It's going to be E. It's going to be, it had to be C or E, D. You could probably guess ahead of time what it was either going to be the choice between B or D or C or E, right? Because those are the ones that have the same critical value but different conclusions. So it's probably going to be one of those two pairs of options. All right. Questions on that one at all? Probably very quiet today. It's Monday, I know.
Don't we want the critical value to be, like if it's greater, don't we reject it?
The critical value in this case is the 4.3, right? That's the one we're trying to compare it against. So it said the test statistic was 4.1.
Mm-hmm.
So it's smaller.
Oh, okay.
Yeah.
Yeah.
Yeah. Yep.
I had them backwards.
Yep. Yeah, the test statistic in this case is smaller. Yeah.
Okay.
Let's look at number 15, 30.15. This one's for proportions. All right, so it's believed that 70% of the population is Democratic and 30 is Republican. Survey of 200 adults where that 122 are Democratic and 78 are Republican. Determine whether the null hypothesis is rejected at various significance levels. I didn't even write. I wrote the number down and didn't write anything down for the last problem. That's all right. 30.15. Okay. Notice it doesn't say whether or not the proportion should be bigger or smaller, right? It just says determine whether the null hypothesis is rejected. So to me, I would infer that they really want us to do a two-tailed test. And I'm going to let P be the percentage of the population that is Democratic. I could have made it just as easily Republican, right? It'd be the same conclusions. All right. So, assuming it's a two-tailed test, then I'm going to need to pick out critical values for the different significance levels because it's telling me at 1%, at 2%, at 5%, and 10%. I couldn't talk and write the numbers at the same time. When I wasn't saying the same numbers, I was having issues. All right. So when we wanted to do the critical values here, remember again, we're doing two-tailed tests, so we're going to split the alpha in half. So for the first one, we want the 0.005, right? So the critical value will be 2.576. We're doing the normal values now because, again, we've got a sample size of 200. For the 0.02 significance, we'll use the 0.01 z-value. So that's the 2.326. I'm just reading these right off the bottom of the T table, by the way, but they have them on the Z table as well. The bottom of the T table has the infinite degrees of freedom, so it becomes the normal distribution. We get 1.96 and 1.645 for the other ones. So those are the critical values that we'll need to compare to. For our test statistic then, remember our test statistic is our p hat, whatever our point estimate for the population proportion is, minus the p, the purported value for p, and then divided by square root of p times 1 minus p over n. So in this case, p hat is 122 over 200. Because we're doing our population proportion of Democrats. Our purported p is 0.7. And so we'll have 0.7 times 0.3 over 200 in the denominator. All right, so on top, we do 0.7 times 0.3 divided by 200. Take the square root and then divide it by 0.09. I get 2.778, if I did that right. I'm using the business calculator, so without order of operations, sometimes you can make an error. So the top should be 0.61 minus 0.7. I'm sorry, I got negative. I forgot that was below. You should get 0.61 minus 0.7 on top, so you get 0.09. I'll just double check my answer here real quick. Yeah, I got the same answer twice, so it must be right. We're going to go with that. Okay. So at all of these significance levels, what would your conclusions be? What would your conclusion be? No matter what, what would your conclusion be? Do not reject? Well, if we're doing a two-tail region, it is, isn't it? If we're doing a two-tail test, it's in the rejection region, isn't it? Because we want, remember, for your two-tail, it's our absolute value of z. Oops, erase. Or don't erase. Our absolute value of z is greater than the 2.576 or the rest of them, right? So we would reject in this case at all the significance levels. So in particular, we rejected the 0.01 level. Remember your two-tailed test, you're looking for greater than or less than the negative. Had it been a one-tailed test for above, then yeah, we would not have rejected. But it had been a one-tailed test below, we would have rejected. So you gotta pay attention to what the tails are. Oh, okay. Let's see, is there one here with a difference? Yeah, let's look at 30.25. Got average claim sizes from two different territories. They've taken small samples from both the territories. However, they assume that the claim sizes are normally distributed in both territories, and the variance of the claim sizes is actually identical in both territories. Remember, for the small sample sizes, we want to assume that to make things easier on us, when we assume that the variances are equal, we'll use the pooled variance for the variance estimate. If we don't have that the variances are equal, we don't pool them, but we have to use the much lower degrees of freedom with that really nasty formula for the degrees of freedom. Remember the Welch's T degrees of freedom formula? Or at least remember where to look it up in your book, I should say. Probably don't actually remember the formula. There's fractions and things squared and all sorts of nasty stuff. All right. Anyway, the reason why they're setting it up this way is so that we can do a pooled variance idea. So we have our null hypothesis is that the means are the same versus the alternative hypothesis that the mean from B is actually bigger. One tail or two tail in this one? One tail, right? Okay. So we've got small sample, but we're assuming the variances are equal, which tells us that we are going to use a t statistic. How many degrees of freedom are we going to have in this one?
The like the n plus n minus 2.
Yep. So in this case, it'll be what? 16? Good. All right, cool. So 16 degrees of freedom. This one is asking us about all sorts of things from 0.5 to 5% significance. So I'm just going to write down the values from the table. If we go to 16 degrees of freedom, we have 2.921 for the first one, 2.583 for the second, 2.120 for the third, and 1.746 for the fourth. These are all from the t-table. I didn't write very good notation there, but they're all from the t-table, right? These are the significances here, the alphas. All right, so again, to be able to do the t statistic, we need to get our pooled variance, and then we have to take that and put it basically in the denominator for the test statistic, right? So our pooled variance, again in this case, will be what? Or how would we pool the variance? What do we do? Yeah, n minus 1, so we'll have the 9 times the variance of the first one, so 5,000 squared, right? Because they give us standard deviations, correct? And then plus, yeah, so 7 times the 4,000 squared, and then divided by the 16. Remember, again, the pooled variance is a weighted average of the variances, right? We have 10 items from A that we sampled, 8 items from B that we sampled. We lose a degree of freedom for each of them when we're talking about sample variances, so that was why we used the 9 and the 7. But those are the weights that we'll use for those variances, and then divide by the number of degrees of freedom, whatever that happens to be. 9 times 5,000 squared. And then 7 times 4,000 squared is huge. Yeah, this calculator doesn't like it. gave it to me in scientific notation. That's how much the calculator didn't like it. Of course, I'm using one of the business calculators, so. Oh, no, that's not right. I screwed that up. I forgot. It doesn't do order of operations. My apologies. That's not the right number. 9 times clear. 9 times 5,000 squared. That's better. 21,062,500. That's better. Is that what you got, Sydney? Okay, cool. I forgot. I did the times and the squaring on the end of it when it doesn't do order of operations. So the business calculator is a wonderful calculator if you're doing stuff with financial math, and it's a terrible calculator if you're trying to do anything else. So for those of you who are taking theory of interest next semester, you get to use the crappy calculator. Not if you're going to take the test. You're going to want that one. I mean, you're going to want both, actually. You can take both into the test, but you're going to want this one for doing a lot of the problems.
Is that like the standard scientific one that most high schoolers have?
This one? No, this is the one that does all the financial stuff like present value and.
Yeah, I'm just buying another calculator.
Yeah, it's only like $20. Yeah, they're not bad. Yeah.
I'm keeping track of it too. I am now.
I'm sorry. But you're going to want to take two in with you in the exam, I promise. You're going to want the one that you have and this one.
Okay.
For that exam, and you can take them both in.
So you want 50 right now.
That's quite the deal.
Okay.
For him, yeah. All right, so we're checking to see if B is bigger than A. So we'll do mean for B, 7,600. Minus mean for A, which is 5,000. And make a really scribbled mess there. And then divide by the square root of your pooled variance times 1/10 plus an eighth. Again, this is supposed to remind you of your variance over n for each of them and add it together, right? Because when you have independent variables, you would add the variances together. But in this case, we pooled the variances, so we've got to multiply that same pooled variance times each of them. It's just pulling out the common factor. It's the same formula. It's just using a single number for it. So did you already do that one? Did you? Oh. I just figured you had. I'll let you do it. I'll be lazy and let you do it. I mean, if anybody else has it, I'll take it too.
$1.194.
Okay. So 1.194 would tell us that it'd be option E, right? We got the accept H naught at 5% significance. Because it's certainly not bigger than any of those significance levels that we had looked at. Is that one okay? All right, let's look at one out of the book. What we haven't done yet is a test for the variance, which we talked about last time, but didn't get to do much with. So let's look at, this is 7.4-2. Y is the weight of a baby boy born at home in Ottawa County. So they give you the weights for 11 boys, and we want to test the variance is 525 squared versus the variance is actually less than that, based on the sample we're given. So to do that, let's get into Excel here. They give us a sample. The numbers are 4082, 3686, 4111, 3686. Oops. 3430, 3289. What did I do? I didn't go all the way across, did I? 3175. Should be fun. 4139. 3289 I already typed in. 3657. 4082. Which one did I miss? There's 11 of them, right? Oh, I missed another 3686. There's 3 of them. Okay. Just random. Oh, I didn't zoom in again, did I? I know I didn't zoom in when I can see Sydney squinting. I don't know why the pause button is in the middle of the screen now on the recorder. I have zero idea why it's sitting up there. Anyway, so I want to test the variance. So remember that we want to use the chi-square statistic if we can, right? So the first thing I'm going to need to do is the sample variance. So if I do the variance of the sample, so I just use the var.s function in Excel. I mean, the variance of the sample is 116,338.9. Remember again that the variance of the sample, the sample variance when we multiply by n-1 and divide by the true variance should be chi-square distribution, right? With 10 degrees of freedom. Okay. So our test statistic then, see if I can copy this over so to try to remember it. Our test statistic will be, don't need that, so should be 10 times our sample variance and then divided by what we think the true variance is. That'll be our test statistic for doing the testing our variance of the population. So in this case, when we do this, we look at the chi-squared table. What did they tell us in the problem? I forgot already. We're doing a one-tailed test that is less than 525 squared, right? And we want the alpha is 0.05. So if we look at the chi-squared table, we want less than the 0.05 on the left tail. So we need to look at the chi-squared 0.95 value in the table. So I look at 10 degrees of freedom at the 0.05 column, so the chi-squared sub 0.95, and get 3.94. And if you do the calculation or a test statistic, what do we get in this case? 4.22. Now, again, the way this was set up, the reason why I used the chi-squared 0.95 was because they said that they were testing the variance to be less than the given, right? So we wanted the left tail. So the left tail was that 0.975 part. So and in this case, we would want that test statistic value to be less than the 3.94 to reject, and we don't have that, right? So we would say do not reject in this case. We agree with that? Okay. So, the second part of this, is this one okay, by the way? Sorry. I should have asked that before I was going on to the next part. Is this okay? Do we all understand where this is coming from? Where the test statistic's coming from? We know that when we do n minus 1 times s squared over sigma squared, that should be a chi-squared distribution, right? So we calculated that sample statistic and got that it was above the 3.94. So we would not reject in that case because we were going to the left tail in that one. All right, so what does it say? Exercise 7.4. I don't see a 7.4. I was going to do the one with testing the equality of the variances. Does it mean example 7.4? No. I don't know where they have the variance for the girls. No, it's in 7.1. They wrote the wrong exercise. It's the previous exercise. So they want to test whether or not the boys and the girls are actually equal. I wanted to do that equality one because we haven't talked about the equality one yet for a test. So it's exercise 7.1, 7.4-1, not just exercise 7.4. I was very confused because that's not how they label the exercises in the book. All right. So let's do the variance for the girls. So 3119, 2657, 3459, 3629, 3345, 3629, 3515, 3856, 3629. All right. Okay, so we got the sample variance for that one. So for the sample, or excuse me, for whether or not we want to reject the notion of the variances being equal to one another, we want to do that F statistic idea, right? So if we do the sample variance for the boys over the sample variance for the girls, we would divide both of these by their individual degrees of freedom, which in this case they're both 10, right? This would be your F statistic, right? Now, of course, the 10s will cancel in this case. It makes it a little bit simpler. Our variance for the boys was the 116,388.8545. And for the girls, we've got 113,108.4909. One point zero three. Okay, cool. All right, so we would look up our F table. They asked us for a two-sided alternative hypothesis, which of course if we just want whether or not they're equal. We're testing at the 0.5 level, so we'll split that in half and make it 0.025 since we're doing two-tailed. The critical value, our F sub 0.025 for 10 degrees of freedom in both the numerator and the denominator is 3.72. Pretty much in your F tables, if you've got something that's a 1 for your test statistic, you're not going to reject. It's just too small. Most of these values, there's a few that'll pop up in the 1s, but notice it's all the way down at infinite degrees of freedom. Okay. So our critical value in this case is 3.72 on the high end. If you would have flipped it, it still would have been the same idea because it's either high or low. I guess we should probably look at the low end. Remember how we do the low end? We had to do the reciprocal and flip the degrees of freedom. Right? Pardon me. That's certainly less than 1. So that 1.03 is not going to get rejected. Or it's not going to be enough to reject anything. So what does that help us with besides the fact that we did a test that we hadn't done a test before? Well, remember when we do our t-tests for doing whether or not means are equal, or the difference of the means is 0, we assume equality of the variances, right? If we don't have equality of the variances, then we have to significantly lower our degrees of freedom and use that Welch's T to be able to do the hypothesis test, right? In this case, however, would we reject the notion that the variances are equal? Is this a reject or a do not reject based on these F values? It's a do not reject, right? This is a do not reject idea, isn't it? So we would not reject these. We would not reject the null hypothesis that the variances are equal. So we might as well go on with the assumption that the variances are equal and use a normal t-test, which is what you would do in part C for this particular problem. That's where that was going. All right? All right. So you got some homework problems to do out of the first few sections. I'll give you a few more to do out of the latter 2 sections next time. And then we'll get into section 7.5